Okay, so there's one more topic we haven't done yet in particle kinematics. So this is the last topic in particle kinematics in non-rotating coordinate systems. Rolling without slipping. Um, and to understand the way this works, I think it's helpful to think for a second about what it means for something to slip. So imagine a wheel rolling along the ground. What would it mean for that wheel to slip? What?
It's friction. Stopped it from.
Well, we haven't talked about any forces yet, so we can't do it in terms of forces. Yep.
Maybe it just means like if it were to kind of veer off a little bit to the side, not be in a straight.
So, and we're going to think about this in one dimension. So there's none of that yet, although that is a thing. Yep.
Is it like the surface of whatever's rolling is in constant contact with the ground?
Yeah, that's the kind of thing that I'm thinking of. So, this is not English. Think of what is slipping.
Or like you can't move without rotating?
Yeah, so think of these two requirements, and I think this will make sense. So the first one is that the point of contact has velocity parallel to the ground. Okay, so if something's rolling, and you look at the point that's in contact with the ground, and that point has a different velocity than the ground, you can think of that as like a definition of slipping. That sort of makes sense, right? And then we're going to think of the same thing, but with acceleration. It's not quite as intuitive, but I think it sort of makes sense to you if you think about it. The point of contact has acceleration parallel to the ground. Okay, what about the requirement that it's parallel to the ground on these? Well, for one thing, you could think of like if bouncing isn't the same as slipping. So if that point that's in contact with the ground has like a vertical velocity, that's not exactly what we would call slipping, And so we'll think of that with acceleration too. So all we care about is that point in contact, we care about its velocity and we care about its acceleration compared to the ground. Okay, so rolling without slipping, the definition we're going to use is the point of contact. I mean, I'm basically just saying the same thing again, but the point of contact has zero velocity. And just to sort of be complete here, I'm going to say this is relative to the ground because, imagine something rolling on a train, on the floor of a train. The ground it doesn't really, that point that's in contact with the floor of the train doesn't have to have zero velocity relative to the earth. It just has to have zero velocity relative to the floor of the train. Okay, point of contact has zero velocity relative to the ground, parallel to the surface. And the point of contact has zero acceleration relative to, sorry to make your notes ugly, but let's correct this. Let's make a distinction between the ground and the surface. So I'm going to change this to surface that it's rolling on. I'm going to change this to surface. I'm going to make this surface. So really what the ground is doing, the way we think of ground, is like some pretty much inertial reference frame that we reference everything to. We don't really care about that. All that matters here is the surface that it's rolling on. Parallel to the surface. Okay, so those are the requirements for something to be rolling without slipping. And I used to make everyone be able to go through the derivation of how this works, but it has some little subtleties and stuff. I think we're gonna not spend the time doing that. We'll talk about how to confirm it once I give you the formula, but we're just gonna think about it like this. If this is your surface, and this is the object that's rolling on the surface, we're always going to define our coordinate system with the y-axis straight out of the surface and the x-axis along the surface. So this coordinate system aligned with the surface is important here. And we're going to call positive angular velocity and positive angular acceleration counterclockwise. You can think of those as positive z angular velocity and angular acceleration. So this is the direction of positive omega and positive alpha. If it's rolling the other way, then those are just both negative. And if you use this definition, then the velocity of the center is equal to negative omega times the radius of the wheel or ball or whatever, 0, 0. And the acceleration of the center, that's relative to the surface, is equal to negative alpha times r, 0, 0. You probably saw those at least in passing in Physics 1. Do those formulas look familiar? Well, you have to be those also are formulas that you used as tangential acceleration and velocity in circular motion. This is something a little different, even though we'll see the relationship between them.
Or is the radius, right?
Radius of the wheel or circle or ball or whatever, yeah. And what I want you to notice here, okay, so first thing, I'll just say, you don't have to write this down, but what if omega and alpha were going the other direction? Then they'd both be negative, and what you'd get is that the center of this wheel would have a velocity in the positive x direction, and the acceleration would be in the positive x direction.
What would happen if the incline was in the opposite direction, right? It was
Yeah, the incline doesn't matter yet because we're only doing kinematics. Okay, so there's no gravity or anything that we're concerned about. We're just describing motion. So this incline could be any direction. What matters is just that positive omega, positive alpha is counterclockwise. Okay, and the orientation of the coordinate system. Okay, so notice there's two things here. Oh, these are the things that I've already been belaboring, but we'll get them down. The first one is that the coordinate system is always aligned with the path for this to work. Once you use this rotated coordinate system that's aligned with the path to get these values, then you could use a rotation matrix or whatever technique you want to convert to whatever coordinate system you want. You're not stuck here permanently or anything. But to use these formulas, you have to use this coordinate system. And then the second thing is that omega and alpha sign convention is that counterclockwise is positive. Yep.
For the sign of the matrix of the acceleration and the velocity of the center,
Mhm.
is it purely based off the direction of the angular acceleration of velocity? Or is it that in relation to the coordinate system?
Well, there's two things going on. There's the rotational stuff and the translational stuff. Like basically, this is a way to relate rotational motions to the translational motion of the center. And so we kind of have two sign conventions. The first one is counterclockwise is positive for the rotational stuff. And the second one is this coordinate system.
Oh, so you apply the coordinate system for the values when you're going to the like BC and AC?
So yeah, you'd apply counterclockwise positive coordinate system to get your omega and alpha. And the result would be that these vectors are translational velocities and accelerations of the center in that red coordinate system. Okay. Okay, we didn't derive this. We didn't derive these formulas. But we can confirm them. So to do that, let's think of, I'm not going to worry about I'm just going to put it on a flat surface. And the coordinate system then looks like this. The y-axis is pointed out. The x-axis is along the surface. And this is the center. And I'm going to call this point, I'll call that A. And I'm going to assume that we have a positive omega and alpha. And what we're going to do is use these formulas that I gave you and prove that the horizontal velocity and horizontal acceleration. Oh man, my computer's mad today. Come on. So what I'm going to show is if we use the rolling formulas above, the horizontal velocity and acceleration are both 0. Okay, so you understand what we're doing here? This is kind of a nice little, a lot of times derivations are hard, but if somebody does the hard work of the derivation for you and gives you the formulas, verifying formulas often is easier. That's especially true with differential equations. You know, coming up, solving differential equations is super hard, but just taking the derivatives, plugging it in, seeing that it works is easy. And this is another case where we're going to do that. Yep.
So in your writing, you say proving that the horizontal velocity are both zeros at the horizontal velocity and the horizontal acceleration.
Oh, yeah. Thank you. Man, oh man, what is going on with this thing? Horizontal velocity and acceleration are both 0. Okay, so basically we're assuming this motion, and then we are going to calculate the velocity and acceleration of A. So anybody have an idea how to do that? Yep.
I just had a question on, so the horizontal velocity and acceleration for the point A is gonna be 0, but for point C?
Yeah, for point C, it's going to be this.
Oh, okay.
Okay. So that's what we're going to do is we're going to assume that the center has this motion, and we're going to use that to calculate the velocity and acceleration of the point A. And the horizontal components need to be 0, or our definition of rolling without slipping is violated. Okay? So
We use like the formula relating C to A.
yeah, exactly. The relative motion equations. That's what we're going to do. Okay, so we're going to say that the velocity of A relative to the ground is equal to the velocity of A relative to the center plus the velocity of the center relative to the ground. This is where we're going to plug in our formula from above. How are we going to calculate the velocity of A relative to the center?
We know that, oh wait, is point A the point on the ground or a point on the circle?
It's on the circle.
Okay.
It's the point on the circle that's in contact with the ground. Yep. So all this, the velocity of some point on a circle relative to the center is just circular motion. Okay, so we're going to go, so the velocity of A relative to C is equal to omega as a vector crossed with the R vector. That's just circular motion. What's our omega vector? So we just have this angular velocity written as a scalar, but notice that that's a positive omega scalar. We're talking about according to the right-hand rule, an angular velocity vector in the positive z direction coming out of the board. And so this is 0, 0, scalar omega. And r is from the center of the circular motion to the point that we care about.
So 0, negative r, 0.
Perfect. 0, negative r, 0. Everyone with me on that? And so velocity of A relative to C is equal to 0, 0, omega crossed with 0, negative r, 0. And what we get is positive omega r, 0, 0. Okay. Now we can use that's the velocity of A relative to the center. The velocity of the center relative to the ground. Oh my God, this is about to crash again. If we have to go through this whole class crashing. The velocity of the center relative to the ground is just this. So the velocity of A relative to the ground is omega r, 0, 0, plus negative omega r, 0, 0. That's the formula. And it's that. So the velocity formula works. Okay? Now we're going to do the same thing with the acceleration. What did I write? So next we're going to do the acceleration. So the acceleration of that point A, we're going to use relative motion again. The acceleration of A relative to the ground is equal to the acceleration of A relative to the center plus the acceleration of the center relative to the ground. This is the formula. This is circular motion. So the acceleration of A relative to the center, what equation do we use here? It's just straight circular motion. Yeah, watermelon equation. So we have alpha cross r plus omega cross quantity omega cross r. Our alpha, what is that as a vector? Positive z, yep. 0, 0, alpha. And we already did the other two, so those stay the same. This is 0, 0, positive omega. And r is 0, negative capital R, 0. And so the acceleration of A relative to the center is 0, 0, alpha, crossed with 0, negative r, 0, plus 0, 0, omega crossed with the quantity 0, 0, omega cross 0, negative r, 0. Okay, so this one comes out to be positive alpha r, 0, 0. This intermediate one we already did above, and that came out to be omega r, positive 0, 0. And now we'll do this one, and we get 0, positive omega squared r, 0. And so our acceleration vector is positive alpha r, positive omega squared r, 0. And now we use the relative motion equation. So the acceleration of A relative to the ground is equal to alpha r, omega squared r, 0, plus the acceleration of the center relative, from the formula, which is negative alpha r, 0, 0. And what we get here is 0, omega squared r, 0. So this one might be a little different than you expect at first glance. Remember, the velocity vector we got for that contact point was totally 0 everywhere. This one has a y component. But remember that from our definition of, what does it mean to slip? Slipping means that there's an acceleration parallel to the surface. So for this to slip, there would have to be a non-zero x component. Okay? So this works. Although it's worth noticing that that contact point does have a vertical acceleration related to centripetal acceleration. Okay. Look at me. I don't bike anywhere. Look at me. I'm a big tub of goo. But I used to bike to school every day, all through the winter. I would bundle up and bike to school all through the winter when I was a much younger man. And my feet would always get way colder than my hands. Okay, so why is that? Why do your feet get colder in the winter biking than your hands? Neither of them are really doing any exercise or anything. It's not because of that.
You're pedaling and your arms are stationary on the bike?
Yes, but so what is it about? So what we care about is the velocity of various parts of your body compared to the ground, right? So is there some reason that your feet are going faster compared to the ground than your hands? Say you're biking 15 miles an hour, your hands are going 15 miles per hour. How fast are your feet going? Okay, so let's calculate that. Okay, so I'm going to just simplify this to the following question. For something that is rolling without slipping, and I'm going to think of this as the the radius of the crank arms, pedaling, the pedals, basically the radius of that circular motion. And I'm going to call that R. And I'm going to say that we're following this circular motion with just a constant angular velocity of omega in this direction. And we're going to calculate this time the velocity of this point B. Okay. So how does this relate to pedals on a bike, your feet on a bike? So what's happening is we're imagining that this surface is moving with the speed of the bike, say 15 miles an hour. And then in addition to that, there's a circular motion of the pedals relative to the bike. Okay. So whatever speed we see for this point B is going to be in addition to how fast the bike is moving. Okay, so the velocity of that point B relative to the ground is equal to the velocity, this is the center, of B relative to the center, plus the velocity of the center relative to the ground. And this is going to come from the rolling without slipping equation. This is from the formula. This works exactly the same as the last example we did. This is circular motion. And so what we already figured out is that the point on the bottom of that circle is moving at the same speed as the surface. What's the point on the top going to be? Its speed compared to the surface. So the velocity of B relative to C
would be the same as the point contacting the ground, right?
It's going to work similarly, but let's do it and see. So this is going to be omega cross R. Omega is equal to 0, 0, omega. The R vector is from the center of the circular motion to the point that we care about. So what's that R this time? Last time it was 0, negative R 0. What is it this time? Yep, 0, positive R 0. And so the velocity of B relative to the center is equal to 0, 0, omega crossed with 0, R 0. And this time we get negative omega R 0, 0. And so now we can do relative motion. The velocity of B relative to the ground is equal to negative omega R 0, 0. From the formula, the velocity of the center is also negative omega R 0, 0. And so add them together and you get negative 2 omega R 0, 0. So the top of a wheel is always moving twice as fast. Again, remember, just be careful, this is relative to the surface. as the center. Okay, so every time your feet come over the top of a pedaling motion, they're going considerably faster than your bike, than your hands, than anything that's stationary sitting on the bike. Okay, and so it's a lot more wind chill, and that's why your feet get so cold on a bike.
Does that not get canceled out by the fact that your feet pretty much stationary whenever you get the bottom of the pedal?
So right, great question. Maybe it does. Maybe this example doesn't make any sense, to be honest. But that's my guess at why your feet get cold. It could just be like, no, you don't have as good a circulation in your feet as your hands. Who knows? I don't have all the answers.
So for velocity of B relative to G, using the equation, is that just like the V center equals negative omega R equation, or
This one where I'm adding the two vectors?
yeah?
This is the relative motion equation. So we're adding the first term is the velocity of B relative to the center of the circle. The second one is the velocity of the center relative to the ground, which just comes straight from our rolling without slipping equations. Okay, but the most important thing about this rolling without slipping stuff is just seeing an application of relative motion, and circular motion, knowing how to do these calculations, getting a little more practice. But if there's like a take-home message that doesn't require any math, remember that the velocity of the point of a wheel that's in contact with the ground is the same as the ground, 0, and the point at the top of the wheel is moving twice as fast as the center of the wheel. Okay. Or the vehicle that's attached to the axles or whatever, And actually, we used to have a really cool picture of this in the physics hallway. It's been replaced by other stuff now, but it was a photograph where they did the exposure just long enough that you could see a clear distinction between something that's moving fast is blurry and something that's moving less fast is less blurry. And it was a picture of a bicycle wheel, and you could see very clearly that everything was a blur at the top, and things got more and more clearly visible as you went down, and then just perfect visibility of the spoke right at the bottom because it's not moving.
Was this like a photo from the physics department, or was it like
No, it was some from like Physics Teacher magazine or something, But we just had it on display, and I used to like it. Okay, any questions about that? That's really all I'm going to say right now about rolling without slipping. There's a few problems I'm going to give you on that. And then if you have any questions about any of them, we can do them on Monday. Yes?
this one?
Maybe. Yeah, it's probably not there's probably multiple versions of it, but is that, can you see it there?
Yeah, you can't see
yeah.
the spokes on the top, but you can see them on the bottom.
Yeah, cool. Yeah, right.
So
Yes.
you said the point at the bottom of the wheel is not moving?
Compared to the ground, it does have acceleration.
Okay.
And so at the next instant, it's moving a little, and the next instant, it's moving more.
So the instantaneous horizontal
The yes, and actually the instantaneous, it turns out the instantaneous velocity vector is 0. So it has no vertical velocity either. Remember, that wasn't true with the acceleration. The acceleration, instantaneously, it had no horizontal acceleration, but it does have a vertical acceleration from centripetal. Okay, and we're going to use these equations again when we're doing rigid body kinetics, because we'll start to put moments of inertia to wheels and stuff like that. and start applying forces and calculating accelerations and things like that. We'll derive the, who's in intro? James, anyone else in intro right now? We just talked yesterday about, well, we were working on CAD programming, and so we did like a CAD version of sort of a Pinewood Derby car. But when we do rigid body kinetics, we'll do a careful calculation of the equation of motion for a Pinewood Derby car. So you can see clearly like what makes it fast, what makes it slow, that kind of stuff. We'll have it all in a single form. And so are any of you guys old enough to be in Cub Scouts yet?
I think,
Okay, well, too bad, missed opportunity, because if you had taken this class before Cub Scouts, you'd be set. You can try to fake it. Okay, so now we're moving on to particle kinetics. That's the end of particle kinematics. So this is the next topic. And so now we've been just describing the motion in terms of time, position, velocity, and acceleration. Now we're going to introduce forces and masses, the things that cause the motion. And particle kinetics is governed, so particle, underlined, kinetics is governed by one vector equation of motion. And that is Newton's second law. And when I talk about Newton's second law, I'm going to abbreviate it N2L, Newton's second law. So the people who took statics with me, remember, we would fill out the tables and everything where we had the row vector. We had the row vector, the force, the moment. But remember, that was for rigid bodies. When we're talking about particles, there's no moments. There's no such thing as moments. We don't care about that. The only thing we care about is Newton's second law, because there's no change of orientation of bodies. And Newton's second law says the net force, so if you add up all the forces, that's equal to the mass times the acceleration vector. And I want to be explicit about one thing. This, in general, a body's different points have different accelerations. So what point on the body do we care about? Center of mass, exactly. So this is the acceleration of the body's center of mass. If you do it for other points, you'll get it wrong. So F net is the sum of all the forces acting on the chosen body. M is the mass of the chosen body. And ACOM is the acceleration vector of the center of mass of the chosen body. one thing I want you to notice, I've brought up similar things a couple times already in this class. Newton's second law only holds for an inertial coordinate system. Okay, and what that means is your coordinate system is measuring accelerations. And if your accelerations are measured from a coordinate system that's not inertial, then Newton's second law isn't going to hold. So an inertial coordinate system, remember, means that the origin is not accelerating. And second, that the axes aren't rotating. So let me just do a quick aside here. So here's a question. Why can't the origin be accelerating?
Needs a reference point for it to work? As fixed reference points?
That's true, but like, why does it, you know? So I'm just going to give you an example that when you ask yourself about this, you have an example you can refer back to and like remind yourself kind of in what way this thing sort of goes haywire. So imagine that you have an elevator. And imagine that you have a scale and a person on the scale. You'll understand why this guy isn't so happy in a second. And then your coordinate system is defined by this video camera in the corner of the elevator. So this is your coordinate system. And that's watching the motion of this guy. Okay?
He's stationary, right? Using the elevator?
Compared to the elevator. But now let's say that the cable breaks and the elevator is in free fall. Okay? So let's think about putting stuff in Newton's second law. So first I'm going to draw a free body diagram of the person. So there's an outline of the person. What forces are acting? Gravity. So that is, well, I'll call it just mg. What does that scale that he's standing on read if this thing is in free fall? 0. Yep. And so this is it. The scale would read 0. And so now let's put this stuff into Newton's second law. The only force is gravity. Okay. And this is equal to the person's mass. Times. Now, think about what that camera sees as this horrible event is taking place. At instant 1, it sees the person in one location. At instant 2, it sees the person in the same location. At instant 3, it sees the person in the same location. And so the acceleration that that camera is measuring is just 0. Okay? And so the y equation here says negative mg is equal to 0. So this doesn't work. Okay? So think about the, I really didn't have to make it in free fall. I could have just made it a regular acceleration. But imagine a camera when you're trying to remind yourself about the importance of inertial coordinate systems. Remind yourself of a camera that's fixed in an elevator as the elevator is accelerating, and just think through Newton's second law. That's why it doesn't work. Okay?
Like, you know, the animation was like that coordinate at this point, probably compensate for that, right?
Yeah. It's relative motion. So it would be like you'd have to use a computer. So you'd say the acceleration of the person relative to the ground, which is what we really want for Newton's second law, is equal to the acceleration of the person relative to the elevator plus the acceleration of the elevator relative to the ground. And so if an outside camera was watching the elevator, then we could add in this second term, and then we'd have something we could use in Newton's laws. And then, so second question. Why can't the axes be rotating?
Wouldn't that apply to the television? Making the inwards?
Well, let's think through it. So I'm going to just kind of do a similar thought experiment. So why can't the axes be changing orientation? Which is another way of saying, why can't you have a rotating coordinate system? And so for this one, imagine this astronaut centrifuge. It's the training thing that they show in all the astronaut movies.
Would carousel also be like a similar example, or?
Yeah. Yes, but I seem to be using examples that cause the most damage to my people today. So this thing, you know. Okay, so it's going around like this. And imagine that you have a camera that's watching this astronaut wannabe, and it's fixed to this arm, so it's rotating around with this person. So this is our coordinate system here. Okay. As this thing gets going faster and faster, imagine that there's a force sensor in this chair. Okay. So this force sensor is going to read a non-zero force. You can imagine that, right? I mean, does that make sense? You know the feeling of being in a car and going around a tight corner, and you get pushed up against the door of the car. This seat would be applying the same force that your seatbelt or the door of the car would be applying. So this would be a non-zero force. But let's think about what the camera sees. So what acceleration does the camera see?
It doesn't see any acceleration since it's moving quick.
Yep, exactly. So let me just draw the three. I should have done this in the elevator too, but so here's instant 1, here's instant 2, here's instant 3. And the camera at instant 1 is just looking straight at this unhappy person. At instant 2, this person's screaming, the camera can't tell why.
Did you hear the word throw up?
Yeah, that's still not, the camera doesn't care about throw up. It only cares about the motion of this person's center of mass. I guess that might change it a little, but. Okay, so the camera sees the same thing at all three of these instants. Even though, the background is changing and stuff. I mean, this person is moving, but all the camera is doing is tracking the motion of this person's center of mass. And so the camera sees 0 acceleration again. And so Newton's second law, I'm not going to write it out in like a vector form, but it will see a non-zero force that's equal to a mass times 0 acceleration. And that doesn't work. Doesn't fork. Okay, so those two examples are worth keeping in mind as like when you have doubts about this stuff. Those are useful little like rebuttals of your doubts. We need to have inertial coordinate systems to use Newton's second law. The next thing I want to talk about is for every application of Newton's second law, and later for every application of the moment equation that I'll call rotational Newton's second law, you need to draw a corresponding free body diagram. And when I talk about these, I'll abbreviate it FBD, free body diagram. And so I just want to say a little bit about what I want to see in your free body diagrams. This will be familiar to the people who took statics. So the first one is draw a closed outline of the chosen body. And this should have no external objects in the picture. And no internal details. The only thing we care about is that outline that separates the chosen body from not the chosen body. That's the only thing we care about. Okay, so if you're doing a free body diagram of this opera singer, um, you want something like this. You don't want this. Because it's not a closed outline. And you don't want this because all that extra stuff, we don't care about that stuff. You know, let me draw it. So you don't want this because we don't care about the stuff inside the outline and we don't care about anything going on outside the outline. All that stuff is just obscuring what's in the in crowd and what's out of the in crowd, you know? This is all about, so all this closed outline is about this. Like look at these definitions of the things in Newton's second law, and it's all very specific about like whether it's part of your chosen body or whether it's not. And that's why we have to be so, that's why we want to be just so focused on the boundary between what we are including and what we aren't. So that's the first step. The second step is to represent each external load. And loads, when we're talking about particle stuff, loads only means forces. But later when we talk about rigid bodies, this will also mean couples. And it's each external load acting on the chosen object. Okay, and so I'm going to break this down into some categories. There are only two kinds of forces that can act on a body. The first one is field forces, which mainly is gravity. But could also include magnetic fields, electric fields. And besides this, there's only one other type of force that can act, and that is contact forces. Applied to the object boundary by the surroundings. Okay, well, the field forces are usually pretty straightforward to represent. I mean, it's usually just gravity. So that's just going to be a downward arrow with mg acting. The contact forces, we're going to represent a couple different ways. So contact forces, either do or don't have a known direction. For a known direction, draw an arrow in the direction that the force acts or the load acts. And label it with a scalar value or variable. So not a vector value, just a single number that represents the magnitude in that direction. Scalar value or variable. And if it's an unknown direction, then draw arrows in the direction of the coordinate axes. And label that with a vector variable. Okay, I want to say one thing that I sort of glossed over. Notice that when I defined Newton's second law, I said that F net on the left side of this equation is the sum of all the forces acting on the chosen body. But now, notice that when I talked about how to represent them in the free body diagram, I only talked about the forces that are acting on the boundary. I didn't talk about any forces that are happening between things inside the boundary. You know, like, for example, so think about this opera singer, okay? If we're representing the contact forces acting on this opera singer, I'm saying that, okay, there's, besides the weight force, there are contact forces that the ground applies to his feet, okay? But what about, there are other forces going on inside his body. The heart is applying, the blood is applying forces to the heart. The blood's applying, all this stuff's going on inside your body. Why are we glossing over that stuff? Because we're not putting any of that stuff in here.
It's internal, so.
It's internal. So what is it about internal? So yeah, right. It's internal, and that's why we don't put it in. But what is it about internal forces that make it irrelevant to our calculations? They all cancel out because of Newton's third law. Okay, so forces always happen in pairs, So when your blood applies a force to the inside of your heart is also applying an equal and opposite force to the blood, and that pair cancels out. So when you try to put that into Newton's second law, you get 0, okay? But there's one place where they don't cancel out in Newton's second law, and that's where something that's in the in club applies a force to something that's out of that's out of the in club, and vice versa. Okay? Then in this case, the ground is applying a force to our chosen body, and we want that in Newton's second law. But our chosen body is also applying a force to the ground, and we don't want that in Newton's second law because it's not acting on our chosen body. So any internal forces happen in pairs, and we don't have to put them in at all. And that's really lucky because there's a lot of stuff going on inside the boundaries of everything we're looking at, you know. You still have a question, Eli?
No, you answered me.
Okay. Anybody else have any questions?
So then, could you draw a quick example of what it would look like if we don't know which way the vector?
Yeah. So there's a couple ways people do it. I'll show you the way I do it. So if you have, so let's imagine, something like this, where you have a body that's attached to the wall by a pin. Then the free body diagram of the bar, you'd have the weight acting at the center. And up here, we don't know the direction of that force. So I would just represent that like this and give it the variable r that's a vector. You also see, this is how I always do it, but you also see people do it like this. And they'll write this Rx and this Ry, but
That's not what we did in statics, right?
yeah, exactly the same. Yep. So one thing that we're going to use a lot and this is for vector variables. So don't use this when your variables are scalars. Just use them when they're vectors. Or but the notation is f sub a b, and those a and b are just dummy variables. That could be 1, 2, or what, they just represent two different bodies. And the interpretation of this in all my classes is the force on A by B. Okay, so the first subscript is what the force is being applied to, and the second subscript is the body that's applying that force. And one of the saddest things in all of engineering and physics is that not everybody uses this same convention. It's about 50-50. And so you have to be really careful when people use double subscript notation. I think this tends to be much more common with engineers, and physicists tend to flip the subscript. So FAB would mean the force body A applies to body B. So that's too bad. But in all my classes, the first subscript is the body that's being acted on. And the benefit of this we'll see that we use this all the time in things where there's a lot of bodies, and we're coming up with a lot of equations and solving a big system of equations. Newton's third law can be expressed in this really simple way. And that is that FAB is just equal to negative FBA. And it's a really easy way to put Newton's third law into equations. You just make that substitution and, we'll see all that. Okay, I only have one more thing I want to say today, and it's quick. So I want to give you two forces that we'll see a lot with known directions. And we'll do more with these coming up, but the first one is pushing without friction. And the second one is pulling. And you can think of that as like a pulling being applied by a cable. So whenever you see frictionless pushing or you see pulling, those are going to be represented as known direction forces. And then two examples of forces with unknown directions. The first one is in 2D problems. And it's a pin or a hinge joint. And so if you have two bodies that are connected by a pin or a hinge, the force that one body applies to the other one is an unknown direction, and you just write it as like, so let's say this is A and this is B, you just write it like the force on A by B. And in 3D, the equivalent of this is a ball and socket joint. This is a little harder to draw, but so there's one body. There's the other body, so it can rotate around freely inside that socket. And we would represent this as the force on A by B with three axes represented. Anybody have any questions about those? So this was mostly setup stuff, but next class we'll start getting into some calculations and some real things. And this, you can think of all this stuff that we just talked about as stuff you can refer back to when you have questions as you're going through problems.
We have several different types of joints in this. Will we have like
We're in this class, yeah, the joints are going to be a little simpler. In statics, statics is almost a class about joints. So this really all we're going to see is pin and hinge joints in 2D and ball and socket joints in 3D. And then pushing and pulling with cables and stuff. Okay, that's all. Hi.
Yesterday, like, you got there was Tuesday.